So we will today continue with what we had left in the last class. So last class we had established a relationship for the dispersion relationship. This is called as the dispersion relationship, wherein c is the speed of the wave and g is the gravitational constant, then k is the wave number and d is the water depth. This establishes the relationship between the wavelength or the wave period and water depth. So we have already seen that celerity is going to be just L by T, that is wavelength divided by the wave period, and if you substitute this in the above expression, because k is just 2 pi by L, then you will end up with this expression for C in terms of wavelength and period, wavelength and water depth. So now let us examine the variation of the celerity in different water depth conditions. So I would we can consider this as a function of, by examining the function tan h tan hyperbolic of kd, as you can see in this table. So when d by L, which is in the second column, is greater than half, we call this as deep water conditions, under which condition, under which situation your kd or 2 pi by d, 2 pi d by L will be close to greater than pi, whereas tan hyperbolic kd will be approximately equal to 1. In the case of intermediate waters, this d by L will be ranging between 1 by 20 and half, and the corresponding variation for the kd and 2 tan h kd are shown here. So tan h kd will remain as tan h kd in intermediate water depths, which will reduce to kd in the case of shallow waters. That pertains, that is when we say shallow waters, the d by L should be less than 1 by 20 or 0.05. So the speed of the wave will now vary according to the variation of this parameter or the tan hyperbolic kd under different water depth conditions. This is the equation we are examining now, and using in the case of deep water conditions, that is d by L greater than half, you will have tan h kd equal to 1. That will lead us to, on substituting, you will have only C equal to root of GL by 2 pi. So in wave mechanics, any variable like celerity, wave height, wavelength of a wave which is in deep water will be associated with a subscript 0, as you can see here. This is for us to easily identify whether the wave of that particular magnitude of wavelength or celerity, etc., whether it is in deep waters, etc. Later we will also see that suffix b is used for the waves in breaker zone. Now this equation that is 2.31, as we have seen earlier, in which we obtained the expression for celerity as a function of wave period, will now reduce to, as you can see here, from which again C naught is nothing but L naught by T. So L naught will become G into T square by 2 pi, which is, that means the wavelength of a wave which is propagating in deep waters will have a value G by 2 pi into T square, which is just a function of wave period. And similarly your celerity or the speed is going to be just a function of T. So this in case of this can easily be mentioned as written as 5.12 into t square in FPS units or in term wavelength in feet, or as 1.56 t square meters in MKS. So you see that it is quite straightforward to evaluate the wavelength in deep waters, and it is also very easy, but remember that you are not supposed to use this expression for a wave propagating in intermediate water depths or shallow waters, because later we will see that in intermediate waters the speed will be dependent on both wave period and water depth. In deep waters the wave speed or the wavelength is not a function of water depth at all. Okay. So instead of going into the intermediate conditions, we will just move on to shallow water conditions, because in the intermediate water depth conditions the definition of celerity is nothing but L by T, that is wavelength divided by wave period, and wavelength will definitely be a function of water depth. So now we will move on to the other extreme condition, that is shallow water condition, because we have just seen the deep water conditions. In the shallow water conditions I have already mentioned you, it is repeated here. So we are using the same expression here. So tan HKD when d by L is less than 1 by 20 or 0.05, you will have KD equal to KD itself. So hence if you once you substitute here, you see that the celerity in shallow water or the speed of the wave is going to be just square root of g into water depth. So now you see that the wave in shallow water when it is propagating, it is going to be a function of water depth, that is all. It is not going to be a function of any other parameter. So to summarize the behavior of the celerity or the speed of the wave, the relation shows that when a wave travels in shallow water, that is what I was trying to say. Now to summarize, you see that the wave speed is just not a function of water depth, it is just a function of wave period in deep waters. In intermediate waters it is going to be a function of both depth and water depth and wave period, whereas in shallow waters it is going to be just a function of water depth alone. Is that clear? So if you start, so you see that in the case of intermediate water depth, the celerity is going to be function of depth and period, that is I mean the wavelength. And if you start looking at the relationship, it is very easy to derive this expression from the above expressions, that d by L naught is equal to d by L into tan HKD. Okay. Now this is a iterative equation, so you have to solve this equation for the wavelength by trial and error method. It is not a closed form solution to get the wavelength. Okay. So now you see some slight difficulty is there in evaluating wavelength. So in order to overcome this difficulty, you should not use the deep water wavelength, because it is very easy to calculate, and then start using it for intermediate water depth conditions. So if you do so, you may have an error even up to about 50%. This depends on the water depth and other wave characters which you are dealing with. So this can be explained, or this will be seen later with the help of an example. Now you see that here, if you want to determine the wavelength for the deep water, straight away you can use this expression, that is d by L naught you can calculate, because L naught is nothing but 1.56 into t square. So in order to arrive at this value, that is d by L from this using this equation, we are equipped with what is called as wave tables. But these days you can very easily calculate, there are some wave calculators available on the net, you can just simply go and use the wave calculator. So you give the wave period, water depth, it will automatically give you the deep water wavelength and also the wavelength as well as the celerity and all other associated variables, which we will be seeing later. So in the case of wave tables, you have to initially calculate d by L naught, and then from which, using the wave table, you can easily calculate d by L, which we will be seeing once again later. But this is a hyperbolic variation, this curve is quite handy if you want to arrive at the wavelength, and you also come across so many hyperbolic functions in understanding the physics of the waves. Later you will see that the orbital velocities, for example, you have already seen the variation of velocity potential, wherein you deal with the cos hyperbolic, sin hyperbolic as well as tan hyperbolic. So all these functions can easily be obtained from the single figure, wherein on the x axis you have the d by L naught variation. So d by L naught is quite easy to obtain. Once you have obtained the d by L naught value from this picture, you can just use this curve to get all the variables which you need. So from d by L you can straight away get your wavelength. Okay, I hope it is all clear now. Now let us understand why did we derive the velocity potential, and why are we now looking at fluid particles and acceleration. As I said earlier, when there is a potential, once you derive the velocity potential in a particular direction, you are going to get the velocity in that particular direction. So in the open ocean, when you have a pile, for example, when the waves are propagating, we have seen earlier that the velocity potential will be varying along the depth. When the velocity potential is varying along the depth, so will be the horizontal velocity, as well as since we are dealing with the 2-dimensional, also the vertical velocity will be varying. So if you are considering the 3-dimensional, that is the variation of the potential even in the other direction, in the other transverse direction, then the velocity in that direction also will be varying along the depth. And this variation is going to cause the forces acting on the structure. So naturally you have to evaluate the variation of the velocity in order to find out the force variation along the structure. So I hope it is clear now why we are using the velocity potential and why are we deriving the expression for the particle velocities. What we saw earlier is the speed of the wave, that is the speed with which the wave is moving. As a whole, what is the speed with which the wave is moving? That is celerity. But now what are we looking at? We are looking at the variation of particle velocity. That is, again please recollect that we are talking about an oscillatory motion. So when it is oscillating, the velocities also will be oscillating and it will be varying along the depth. So we will get back to the expression. This is the expression which we had derived, and when you differentiate it with respect to x, this is the expression you will be having. But we have already derived the dispersion relationship as stated earlier, and we also know that A is nothing but the amplitude, which is half of the wave height. So substituting in this expression all this, you can easily derive the expression for the horizontal water particle velocity, also referred to as inline velocity, which is going to be a function of wave height. So it is going to be a function of wave height, wave period and water depth. I am not using wavelength because once I said wave period, it is automatically understood that wavelength is included in that, okay, because wavelength is nothing but a function of wave period. So now how does this velocity vary? This velocity, the horizontal water particle velocity, will be varying from z equal to 0 up to the seabed. And how will the variation look like? Remember, all these expressions are for a sinusoidal curve. When you have a sinusoidal wave moving, under this we have already seen that the phase variation of velocity potential will be out of phase, will be a cosine curve, but the horizontal water particle velocity will be a sine curve, that is, which will be in phase with the wave elevation. So you will have sin theta here. Now z will be varying from 0 to minus d up to the seabed. So what does this mean? This means that the velocity, particle velocity, will be a sine curve variation with maximum amplitude when z equal to 0, that is at the still water level z equal to 0, and that is the point where you will have maximum orbital velocity, and the magnitude of which will keep on decreasing as you go towards the seabed, and at each elevation it will be the phase variation will be a sine variation. The same thing holds good in the case of a vertical velocity. So now vertical velocity will be out of phase with horizontal velocity and the eta, and remember there is a negative sign also which will come into existence, okay. So again the phase variation can be obtained here, the phase variation can be obtained here. So at each elevation you can obtain Umax at each elevation, that is on the assumption that kx minus sigma t is 90. When kx minus sigma t is 90, that is the theta, if we assume it is 90, then sin 90 is equal to 1. So you will have the maximum value of u at the crest of the wave, because we are talking about a sinusoidal wave and crest is theta equal to 90, because when you have the wave so this is the variation of eta. So this will be u at somewhere close to the free surface, and then you see that the wave the magnitude of the horizontal particle velocity will be reducing as you go towards the sea, and each elevation it will be a sine curve. Now I am talking only about the magnitude, okay. If I plot that, how does the variation look like? The variation will be like this, because this will be the maximum, that I am plotting only the magnitude here, and then this will be at this. So you see that this variation will be nothing but a cause hyperbolic variation. So usually they will you will be asked how does the particle velocity vary under the progressive wave. You need to say that it is a hyperbolic variation. Is that clear? So now you see that when you have a structure here, the distribution of the velocity is very important in order to evaluate the forces on the structure. So now similarly for W, that is the vertical velocity. So this is what I have explained here. So now we look at the variation, phase variation, which I have just now stated in this plot, how each one will vary. This is the sine curve and u will be 0 at theta equal to 0 and w will be negative. Look at the expression, and then whereas here this will be maximum at the crest u, at that particular point w will be 0 and etc. for the other phase. Okay. As I said, what I drew on the board, the same thing now I am representing here for u and w, considering the 3 water depth conditions which we had already discussed. That is, in the case of deep waters you will have u and w will be almost same, will be same. Then here you see the variation of u, this is the maximum velocity, horizontal velocity at each of the elevation, and similarly the maximum horizontal maximum vertical velocity at each elevation. So this is actually for shallow water condition, that is d by L equal to 0.05. So you see that the horizontal velocity will be much higher. So what does this also imply? If you have a pipeline here, will it experience any wave force? Very negligible. But if you have a pipeline in the shallow waters, the magnitude of the force in the horizontal direction is expected to be almost close to that what can be close to the free surface. So such information is easily obtained from this. So now we proceed further in order to obtain the acceleration. Waves are an unsteady flow, it is an unsteady flow. So the fluid properties vary with respect to time. So when wave is acting on a pile or a structure, the forces induced on the pile will be due to both particle velocities as well as due to accelerations, which we will see later. So in order to obtain the total force, we need to have the particle accelerations also, which are derived, and these are all simple derivations which you can straight away obtain, and this is in terms of h and this in terms of amplitude. Only thing is the difference is just we have used k also here substituted, etc. Is that clear? So we have covered the velocities and particle velocities and accelerations. If I am floating on the water surface and in the deeper waters, then I will be moving from my mean position in circular orbits as like this, okay. And in case I am in the shallow water conditions, then my position from the mean position, my movement will be in elliptical orbits. Is that clear? So this is very important, how the motions water particle motions take place under different water depth conditions, and that is what we are going to examine with this. So since the expressions for the individual, I mean the horizontal and vertical particle, so this can be obtained from integrating the velocities, horizontal and vertical velocity. So you integrate, so you substitute u, look at the earlier expressions, and then you will end up with an expression for delta x, that is the displacement in the direction of wave propagation, that is in the horizontal direction. Similarly, the vertical displacement in this direction is going to be like this. So from the earlier expression, from this expression, let me call this by an alphabet and this by another alphabet as done here. So I have delta x as d into cos of kx minus sigma t, where k is where d is as shown here, and similarly the vertical displacement is given by this, where b is from the former earlier slide you get all this information. Now I just take to this take this sin square and k square, and when I add them, that is equal to 1, which all of us know, from which we get an expression as you can see, which is nothing but the equation of an ellipse. So this is the equation of an ellipse showing that the water particles move in an elliptical orbit, where d is semi major axis, horizontal that is horizontal measure of particle displacement, whereas your b is semi minor axis. Okay. So now as we have examined the shallow, the celerity behavior of celerity in shallow and deep waters, we will go through that process for different water depth conditions. So in the case of a shallow water condition, cos hyperbolic argument will become 1, whereas sin hyperbolic will become the argument itself. So the arguments here is k into d plus z, whereas sin hyperbolic you have two arguments. So you see b and d, so you have to consider these two expressions. So using this these limitations, you will get d equal to this much and b equal to h by 2 into d plus z divided by d. Now you substitute in this, I will get expressions as shown here. This is how, so you see the size of this semi major axis and the size of the semi minor axis, these two are different, proving that the particles in shallow waters as well as in intermediate waters will be moving as elliptical orbits. Okay. So if you physically stand there, you will be undergoing as an elliptical orbit, provided you are in intermediate or shallow waters. But in the deeper waters, in deep waters, d is given by this expression as we have seen earlier, so which can be written as in the form of exponential and when d is very large, the negative exponential e to the power minus k into d plus z and e to the power minus kd will be very small. So you can just simply write this expression as given here, which is nothing but this much, that is h into h by 2 into e to the power kz. The same thing will hold good for B, the other direction of displacement. So you see that both the directions of displacement, when the wave is in a deep waters, particles will be moving in circular orbits, whereas in shallow waters it will start moving in elliptical orbits. So this is what I have written here. The amplitude of the water particle displacement decreases exponentially along the depth, because it is an exponential variation, right. So the decay or the reduction in the displacement for a wave which is in deeper waters will be more drastic, and in fact at a distance of L naught by 2, L naught is nothing but 1.56 into t square divided by 2, at that up to that location only you will have some amount of displacement, beyond that the displacement will be negligible, particularly in deeper waters. In deep waters the displacement will be almost 0, negligible at a distance of L naught by 2 below the still water line. And this is what pictorially represented as shown here. So in shallow waters you see that the displacement will be felt, the horizontal displacement will be felt up to the seabed, the vertical displacement will be reducing as you go below the free surface. So you see that if you have a pipeline here, the horizontal force will be almost same as that near the free surface, okay. Now in the case of intermediate waters, the horizontal displacement also will be reducing as you go towards the seabed. In both these water depth conditions, the particle orbit will be moving in elliptical orbit, whereas in deep waters, as I have explained earlier, at a distance of L naught by 2 this will be almost negligible. Now let us understand how this can happen. Can we have some kind of an animation? The University of Delaware, under the leadership of Professor Tony Dalrymple, who has also brought out a nice book on wave mechanics, he has created animations to clearly visualize the effects of variation of the particle displacements, etc. So let us now look at this animation. Initially I am trying to generate deep water conditions by assuming a wave height of 7 meters, wave period of 8 seconds, propagating in a wave in a water depth of 100 meters. So let us see what happens in this case. So you look at the orbits here, near the free surface you see a large orbit, that is the displacement is quite large near the free surface, and it is all in circular orbit, because your wavelength in this case is close to around 100 meters and the water depth is 100 meters. So the d by L relative water depth is close to around 1, which is greater than 0.5. So deep water conditions, the size of the orbit will continue to reduce as you go down towards the seabed, and it is almost negligible, you see here. So this is how the particles will be moving under the waves when it is propagating in deep waters. So now let us change the parameters in such a way, let us try to see simulate wave in intermediate water depth conditions. So I am assuming a wave height of 5 meters and I am just changing the water depth to 30 meters. So now you see that earlier case there were not much of a disturbance here. Now you see more or less it is circular, but it is tending towards shallower. If you change the water depth, if you reduce the water depth or increase the wavelength, what will happen? Your d by L will reduce. Thereby you can have, instead of circular orbits, the waves will be moving in elliptical orbits. So let us examine for a wave height of about since I am going to reduce the water depth drastically, I am going to reduce the wave height also, because you cannot have a huge wave height, it cannot sustain in a shallow, very shallow waters. The sustainability of wave height we will be looking at when we are talking about the wave deformation. And this one I am changing it to 2 meters. So now you look at the variation, you see that the waves are propagating in elliptical orbits and the effect of these waves are felt up to the seabed. Now one more interesting thing we can observe now. What did we see in deep waters? In deep waters we assumed for 100 meters water depth, we saw that the orbits were only near the free surface and after certain distance it reduced. Now let us try this example. Let us assume that the water depth is 4000 meters. Let me have the wave period about 2 hours. I have said a wave can have only a wave period of up to 30 seconds, but now I am increasing the wave period to 2 hours, say approximately 2 hours, that is 120 into 60, so 7200 seconds. Am I right? What can we see now? So we are talking about water depth of 4000 meters. Now first initially let us restrict ourselves to usual, say 10 seconds wave, normal, under normal circumstances. So you see that in this case the water depth is 4000 meters and a wave height of 0.5 meters. You see that the displacement of the water surface is very small and the displacement the orbit is only near the free surface. Now I change this to 7200 seconds, that is equal to 2 hours. Now you see what is happening in 4000 meters, that is 4 kilometers, you see that the effect of a long period wave is felt even up to the at the seabed. What is this? What we have simulated here is nothing but a tsunami. Tsunami can have wave period ranging up to hours, and that is what we have exactly simulated now. I hope you have understood one of the difference between a wave and a tsunami. Okay. So I am sure that this exercise has given us a very clear idea about the behavior of the waves in different water depth conditions. If you have a sea grass or whatever it is, now this is how the water particle would be looking like, the displacement of or the motion of the individual particles when a wave is moving here. So you will have the motion in this direction and here, so when under the trough the direction will be in this direction, it will be focusing in this, and around this time it will be vertical. So all these things I have already explained in terms of the phase variation, but this picture shows you how a leaf can undergo the kind of motions when a wave is propagating over it. Now we look at the pressure distribution under progressive waves. So as I said earlier, we have been we are dealing only with the linear theory, and we have linearized the Bernoulli equation, which will be used for defining the pressure distribution under the waves. So here is the linearized Bernoulli equation, and the pressure distribution is shown here in this picture. Now we multiply the Bernoulli equation by rho, and then to get the total pressure, and now this will have two components. One is the dynamic pressure component and the other one is the static pressure head component. So we have already seen the expression for velocity potential, which once you substitute you will get an expression for the pressure as shown here. This would mean that the pressure will be varying along the water depth, and it is very important to have in mind how this dynamic pressure component varies and how the total pressure varies. For this purpose, we again look at the expression for pressure, which is rewritten here in this slide, and we know that eta is h by 2 into sine of kx minus sigma t, and this hyperbolic function is represented as defined as pressure response factor, and it is represented as, say, k suffix p. So hence the definition of the pressure head is given by this equation, Kp, that is pressure head, equal to Kp into eta minus z, or pressure alone you just take the gamma into the equation and this will be the pressure intensity. Now we will consider the pressure variation at different elevations within the fluid medium. So at z equal to 0, that is at the still water line, using this expression, this will be the basic equation which you will be using for defining how the pressure is going to vary. At z equal to 0, your pressure will be equal to P by gamma. And next is at the seabed, z takes the value of minus d, and hence P by gamma will become d plus eta by cos of kd. So how will the static pressure head look at the below the crest? Below the crest it will be d plus eta, water depth plus that elevation above the water, I mean mean water level or still water line, So, you will have d plus eta, but the actual pressure will be as indicated here when the crest is crossing, which will be less than the hydrostatic pressure because cos kd, because of the variation of cos kd. That is, cos kd is always greater than 1. Now, under the trough, if you look at, you have to use the same expression with z equal to minus d and eta taking a value of minus eta, you will land up with this expression, and in which case this actual pressure will be greater than the hydrostatic pressure at the crest. So, this is a basic difference when a crest is passing by and when a trough is passing by. So, finally, you have to you have an expression relating the variation of eta and pressure, dynamic pressure. This is why I said that this is one of the basic principle, main principle why it is being used for the tsunami pre-warning system, or the pressure sensor is used for obtaining or measuring the wave climate within in a given site, for measuring the wave climate. Okay. So, here you see that K is just the pressure response factor at the seabed. This it's both are related, pressure and N, and N is nothing but a correction factor adopted, and N takes a value slightly greater than 1, and that is for long period waves. How big the value should be depends on how long the waves are, and similarly for the short period, in which case N will be less than 1, and in the case of linear waves we use N equal to 1. So, thus we have seen the dynamic pressures under a progressive waves. The dynamic pressure, in fact, it will be reducing from the still water level as you go towards the seabed, and it is going to be a cost hyperbolic variation. So, I hope the pressure distribution under waves are clear, and you will get more information about the calculation of these pressures and other how once a pressure is given, how you determine the wave elevation or vice versa in the some of the examples which will be worked out later.